parallel and series circuits. And it's important to have looked at the first lesson in this case, which is basic circuit theory first. Okay, and I'm going to use some of those examples first, just as a quick recap. Here is our circuit. I'm going to draw a nice simple circuit. We have a cell with an ammeter and a resistor. As we talked about before, we have coulombs that are going around this circuit, and they're carrying with them energy. The energy is deposited in the resistor, and then the coulomb comes back to the battery, ready to be charged up again. Let's imagine we have a 3-volt battery supply. So, then what that means is that's defining how many joules each coulomb is going to carry. And in this instance, it will be 3 joules per coulomb, hence a 3 joule voltage supply. It uses up all of its energy in that first resistor and then comes back uncharged, ready to be charged up by the battery again. Excellent. Okay then. Now the ammeter here is looking at the number of coulombs working around this circuit per second. And I'm just going to take an arbitrary value, and I'm going to say it's 3 amps, which means that we have 3 coulombs leaving the battery every second, 3 coulombs moving through the resistor, and 3 coulombs moving back into the battery every second. Now, this is where we're going to come up with a new idea. If I was to attach a voltmeter about this component, then what the voltmeter is showing me is the voltmeter represents, it measures the electrical potential energy here compared to the electrical potential energy after the component. In this case, before it's at 3 joules, and afterwards at no joules. So what we say is it's measuring the potential, the electrical potential difference, or the PD, which is measured in volts, but it's called a potential difference. And in this case, we have 3 joules on each coulomb that's being used up. So in other words, that is 3 volts, because that's how we define the volt. Excellent. One last thing to cover, and that's the concept of resistance. Okay then. Now what resistance, we have some equations that we can deal with to work out resistance, but I'd like you to intuitively try and understand what it means. And what resistance is saying is how many volts is needed for 1 amp to flow. In other words, how many of these joules are needed, how many volts are needed, in order for 1 amp to flow through the system. In this case, I have 3 amps, and 3 volts are delivering that. So therefore, in order for 1 amp to flow, I must have 1 volt doing so. So in this case, I'd have 1 volt per amp, which is the same as saying 1 ohm. So just remember, resistance says how many volts do I need if I just want to create a 1 amp flow across it. Okay, last point, which is a revision from the last lesson, will be the power. In other words, the energy delivered per second by the battery. And if we remind ourselves that each coulomb takes 3 joules, and I know, because of my current, I have 3 coulombs that are pumping out of the battery per second, 3 coulombs going through the resistor per second, and 3 coulombs going back into the battery per second, then essentially my power is 3 coulombs times per second times the 3 joules, which gives me 9 watts of power. Excellent. Okay, now let's get on to the title bit. What's happening in a series and parallel circuit? So let me draw for you a series circuit. Now the useful thing about this is that I'm going to use all the same components as I used in the first example up here. So I'm still going to use 3 volts in my circuit. I'm going to use the same value of resistor, but this time I've just increased them into a series circuit. So let's talk about what's going on here. Here comes my Coulomb. It comes out of the battery fully charged, and if you'd like to use this analogy, if you like, that it comes around and it sees that it's got to get over 2 obstacle courses. Not one like it did before. It can't give up all its energy to the first one, otherwise it'll have nothing to get through to the second one. So therefore it gives up some of its energy before giving up the remainder of its energy on the way back. So we have 3 joules to start with, because it's a 3-volt supply. Comes around, and because they're the same resistance, it can give up half of its energy to the first one and half of its energy to the second one. So that must mean where it entered with 3 joules, it has 1.5 and 0 joules on the way out. Brilliant. Now, let's just look at the potential difference acting on each of those resistors. In other words, what it's asking is, what's the electrical potential difference per Coulomb from this point here to that point there? And hopefully you'll be able to see that it's 3 minus 1.5, giving us 1.5 volts. Okay, what about the other side? We've got 1.5 joules on the Coulomb here and nothing on the other side, so we should get another 1.5 volts. So surely, I hope it makes sense that what happens is the energy that comes out of the battery is shared between the 2 components before coming back to the battery again. Okay, now because it needed the 2 obstacle courses to get over, it has to travel more slowly around the circuit. And because we've got double the amount of components, or double the resistance, therefore the current is halved compared to the first circuit up here. Fantastic. Let's just put, just to make sure we've got a complete measure of this circuit, let's look at the power output as well. Well, we have 1.5 coulombs per second coming out of the battery, and each one's carrying 3 joules, so therefore my power is going to be 1.5 times 3, which gives me 4.5 watts of energy. Excellent. Okay, now let's turn to a parallel circuit. And once again, I'm going to use exactly the same components, but place them in a parallel combination. I'm going to place ammeters on each branch so we can see what's taking place. The resistors are identical, the same cell is placed in, so now what happens? Okay, the Coulomb comes out of the battery. It comes around and then it hits a junction. It has 3 joules, of course, it has 3 joules all around because we've got a 3-volt supply. But this is the thing, it doesn't split, it makes a choice. So at this point here, a choice takes place. And when I say it makes a choice, in actual fact, these coulombs are shoulder to shoulder, so it just shunts along and it shunts as many that can get through here and as many as it can get through there. However, if it's travelling along here, it comes in at 3 joules, uses up all its energy in that resistor and comes out empty and goes back to the battery again. 0 joules, 0 joules. So in effect, it doesn't see, each Coulomb does not see that branch. So it's really behaving just like the original circuit did. Each Coulomb only sees that circuit in front of it. So what we can say is that this will be rushing around just like it did in the first circuit at 3 amps. Excellent. Okay, what about the Coulomb that comes down here? Well, it has 3 joules on it again, uses up its energy as it goes over the supply, and once again, it only sees the circuit in front of it, which is identical to the first circuit. So therefore, it travels around at 6 amps and heads back to the battery with no energy on it. Of course, if we've got 3 amps coming through this way and 3 amps coming through this way, that's going to mean there's going to be many more coulombs coming back to the battery. So this must be an addition of both currents. Now that is not an easy thing to work out, so that is something which people trip up on often. Okay, shall we take a look at the voltage this time? Or should I say the potential difference? looking at this branch, it comes in with 3 joules, and then it uses up all of its energy and leaves nothing. So the electrical potential here to here, the difference between the two, is going to be 3. And again here, the electrical potential difference between these 2 points, because it comes in with 3, loses it all, and has 0 afterwards, is 3 volts. Let's just for completion, just write in the power of the parallel as opposed to the series. Here, if we take a look carefully, 3 joules are on every coulomb that comes out of the battery. But how many are coming out of the battery? Well, it's the addition of these 2 branches here, which are 6 amps. So 6 coulombs per second are coming out of the battery, carrying with them 3 joules each. So therefore we have 3 times 6, giving us 18 watts. That's quite huge, actually. And that's why, even though if you plug in lots of light bulbs in series, they dim because each light bulb's getting delivered fewer joules. Whereas if you put them in parallel, they're all the same brightness, but it drains the battery quicker because more energy is coming out per second. Interesting thought there. Anyway, there are some rules about series and parallel circuits, which I just want to jot down. Let's look at parallel first, and then series after that. And we're looking at the current and the potential difference. Okay. So, in a parallel circuit, the one we have here, the current actually divides up. So it's shared between the branches. The potential difference, ironically, is always the same as the battery. So therefore, in a series circuit, we have the same current. If you take a look there, the current's the same here, the same there, and there. Whereas the potential difference is shared. So those are the rules of the series and parallel circuits. Excellent. Okay, let's look at a few examples. Let's look at one more example. We have here a circuit which is slightly more complicated, but we're going to apply the same rules as before. We have the same resistors as before. We have the same batteries before. And I'm going to place an ammeter coming in and out of the battery, an ammeter on that branch, and then an ammeter. Let's place it in the middle there. Okay, what's taking place here? Well, simply, the coulomb comes out of its battery, or cell, and at this point it makes a choice. Let's deal with this choice first. Let's imagine it's going along the longer arm, and what I'd call the simpler branch, because it has 3 joules and it uses all of those joules in that resistor. So in essence, we're back to exactly what we had in the first circuit, which gives us 3 amps. Okay, what happens in this part of the circuit, this arm of the circuit? Well, 3 joules is then shared between the 2 resistors. So we're left with 1.5 joules there, and then once it's come out, it goes to 0 joules. And then goes back round to the battery again. Half of its energy used there, half of its energy used there. Because it's gone round 2 of these resistances, its current falls by half the value, 1.5 amps. And of course, because we have current coming through this branch and this branch, we need to add those 2 together to give us 4.5 amps is the total current coming in and out of the battery. Okay, what's the potential difference here? Well, it's used up all of its energy from 3 joules to nothing. What about in this branch here? Well, it's used 3 joules to 1.5, so it's only used 1.5 joules coming through there. And it's used its, again, the same on this side. So you can see, here we have a series arm in which the current's the same at all points, but the voltage has been shared. Here is a parallel arm, which means that the voltage is the same as the first one, but the current has been shared between them. Okay, if we just look at the power as well, I've got 4.5 coulombs per second coming out. Each one's carrying 3 joules, so 4.5 times 3 should give me, oh, I'm going to have to do that quickly in my head, 12 by 1.5, 13.5 watts. If I were to, well, maybe you would like to try the next example. So if you want to, you can hit pause after I've drawn the diagram for you. Just make it even more complicated this time. We'll put an ammeter in here as well. And then again, on the bottom side, just the one resistor. So if you want to give this a go, then find the current in these 3 positions and the potential difference across each of the resistors. And if not, then I will go through, and we have a 3-volt supply, of course, and all the resistors are the same as before. Okay then, right, let's go through the solution nice and quickly. Coulomb comes out, it's full of 3 joules because it's a 3-volt supply. It makes a choice. Let's make the easier choice. It goes down here. Coming in 3 joules, uses up all of its energy, and then comes out and goes back to the battery with 0 joules in it. It's the same, this Coulombs is the same as the original circuit, the same as this next circuit. And so therefore it goes across at a speed of 3 amps as before. Going across this circuit here, the choice here comes in with 3 joules. It's got 3 obstacle courses to get over. So now it uses only a third. It uses then 2/3 and then finally comes out with nothing. So therefore what we have is we take, it uses up 1 joule in the first one. It then uses up a further joule before it uses up all finally. No joules at the end. 1 volt, 1 volt, 1 volt. And because it's going across 3 of them, it's slowed up by a third 1 amp, meaning our total current is the addition of this and that, which gives us 4 amps. The power, we have 3 joules coming out. Obviously, these coulombs go back. They're coming back into the battery, and they're leaving the battery at 4 amps. 3 times 4 gives me 12 watts. Excellent. Okay. Now, just one last example. A bit of paper. This time, rather than just guessing at what resistance is, I'm going to tell you a resistance, or we're going to work out a resistance. Got a 12-volt battery, and it's 0.5 amps it's drawing. So if you remember my expression for what the resistance is, the resistance is looking at the number of volts required to make 1 amp move around the circuit. Because I've got half an amp moving around the circuit and 12 volts are providing that, therefore I must have 24 volts in order to get 1 amp flowing. So that's our intuitive idea of what resistance is. Or if you like, resistance is voltage divided by the current. Excellent. So let's put the real values into a parallel and series circuit and see what happens. First of all, look at parallel. You might want to try these yourself. You might feel very confident with it now. One branch, two branches. I'm going to use the 24 ohms again, and this time I'm going to use 12 ohms. A 12 volt supply like we do above. So can you tell me what the potential difference will be and what the current is going to be? And I'm going to go through the solution right now. Well, first of all, here comes our Coulomb. It's collecting with it, it's bringing with it, 3 joules, giving all of its energy up to the resistor and leaving with 0 joules, and then trundling its way back into the battery. Okay, it sees exactly what the circuit up here sees. And this circuit's going around at 0.5 amps. Okay, it's also given up all of its energy, so its electrical potential difference from here to here is 12 volts. Hold on, apologies there, I got too carried away. This is coming around with 12 joules on each because we have a 12 volt battery this time. Okay, so it's coming around with 12 volts. If it makes the choice and goes the long way around, it comes around, it's got its 12 joules and it's giving up all of its energy to that battery and leaves with no joules. So therefore we have 12 volts. Remember, in a parallel circuit, the voltage stays the same whichever branch you're dealing with. Okay, you can say to yourself, if you like, that 12 volts, 12 ohms suggests that you're dead on the right ratio to suggest that 1 amp is needed. But let's work this out a little bit more accurately. Current is going to be voltage divided by resistance. 1 amp. And so therefore, if 1 amp of empty coulombs are coming up here, and 0.5 are coming through here, this must be 1.5 amps. Okay, let's look at the series and see how confident you feel with this. Now, we're looking for the electrical potential difference in these two positions and the overall current flowing from our 12 volt battery, 24 ohm and 12 ohm resistor. Now, first of all, you can say to yourself, right, Coulomb comes flying out of the battery, it's got with it 12 joules, I got that correct this time. And then it comes through here, and this presents twice as much resistance as this one. So if you like, you can say twice as much energy needs to be used up in this obstacle course than it does in this one. So if we've got used up twice as much, then 8 joules must be used up here, leaving us with 4 joules remaining before it comes out and is left with no joules. And it goes back to the battery with no joules. Okay, it's a little tricky there at that time, but you've got to look at the ratios. Given that's the case, the difference between 12 and 4 gives us 8 volts. Obviously, the difference between 4 and 0 is going to give us 4 volts. Or you could have worked that out because you could have said, well, the total voltage is divided between the two. And the current here is the voltage divided by the total resistance, which is 12 divided by 24 plus 12, which gives us 0.3 to 1 decimal place amps. Not bad. Lastly, if you were having trouble about wondering how to work that out because the ratios weren't as easy to work out, you could say to yourself, because you knew that we had 0.3 amps flowing through, you could say to yourself that the voltage is going to be the current times the resistance. 0.3 amps times 24 gives you 8 volts.